talk a little bit today about how you can build a planet if you want to build a planet. I'm going to talk about what you need, what ingredients you need, how you put them together, and is it easy? Okay, so what do you need? You need ingredients. Well, the ingredients you've got, the periodic table. Everyone recognizes the periodic table, I hope. This is mostly complete, starting from hydrogen, helium, up to the heavy elements and the radioactive elements at the bottom. So that's the ingredients. So where do they come from? Well, they come from lots of different sources. And I'll go through briefly some of the sources of where these elements come from. So we'll start off with hydrogen and helium, the simplest ones. Well, they come from, as you might expect, the Big Bang. This is a simulation of the Big Bang, not a real picture. They are formed about 100,000 years after the actual start of the Big Bang, when the nuclei come together. And basically, that's all you get from the Big Bang. It's a whole bunch of hydrogen, helium, and maybe a little bit of lithium, but not much else. So it's kind of boring, if you like interesting things. You wouldn't be able to make a planet out of that. So what about all the other stuff? Well, basically, all the other stuff comes from stars. It gets processed in stars, and I'll show you what happens. So for these elements, and there are some particular interesting ones like oxygen and silicon, which are relevant to us making a planet, they come from exploding massive stars or exploding white dwarfs. And this is not a simulation, this is a real picture, time-lapse of an exploding star in the southern hemisphere, so you can see that. Not like this picture, this is a Hubble picture. But this star is actually, it's not really exploded, it's just about to. It's in probably another million years, it will probably go into a supernova, and then you'll see a real serious explosion. But as an example, that's what happens just before you get to a supernova, and basically all these elements are thrown out into space by this explosion. And after it's gone bang, this is the remains, this is what you left over. It's a whole bunch of stuff all these elements have been thrown out into space, and there's not much left of the star, as you can tell. So that's where some of the elements come from. What about the other ones? A lot of them come from, and particularly for us, a lot of them come from dying low-mass stars, stars like the sun, which don't go bang. They kind of slowly blow off their outside stuff and into space, and then sort of die away. So particularly interesting is carbon and nitrogen, because we're made of that. And this is what we're made of. We're made of these dying low-mass stars. And these other elements are also made of that. So here's some examples. This is called the Bubble Nebula, not surprising. And basically a star in the middle has blown off a shell of its outer stuff and into space, and there is still a star left in the middle. You can't see it in this picture. But you get these beautiful, they're called planetary nebulae because they're not really planets, but they just look like they were thought to be planets originally when they were first seen through telescopes. So here's another example. This is called the Helix Nebula, and you can see that, you can see what's happened. The star, as you can just about see in the middle, is basically thrown out all this stuff and into space. So what's happened is the material has been processed in the middle of the star, and basically it's blown it all out. Here's another example. This is where the star, instead of blowing it into a nice ring or a nice sphere, it's blown it into jets. And again, you can really get a feel for what's gone on in this star. This is kind of blowing out this stuff. It's not exploded, it's just blowing out the outer envelope. So that's what we're made of mostly. This junk that's thrown out by the star. But this is not the end of it, because all those explosions of stars doesn't get you the heavy elements, the really heavy elements. And this is where it gets interesting, because only recently, in the last couple of years, have people understood where these really heavy elements come from. In particular, things like iodine and gold and uranium, they're definitely not processed in stars, and there's very little made in supernovae. So people were conjectured, well, maybe it was actually something really exotic, which is merging neutron stars. So a neutron star is what happens when a star explodes, and you get remains of it in the middle. It's basically a very, very dense star, which is almost the mass of the sun, but it's only a few miles across. So it's pure neutrons. These things are pretty exotic. But you imagine something a few miles across with the mass of the sun. It's got to be pretty, you don't want to get too close. So what happens to these things? Well, up till 2 years ago, nobody really was sure about this, but eventually they were discovered using gravitational waves, which is the gravitational waves where basically a wave in space, so the whole of space is curved, it has a wave that goes through it, and it's very recently detected on Earth. And this is a simulation. Basically, you get two neutron stars. They're a few hundred miles away from each other. They speed up, they accelerate faster and faster. This is happening in real time. These are things of the mass of the sun going around at this speed. And then they merge, and then you get something pretty violent. It's violent enough that 1% of the mass of the star gets turned into pure energy instantaneously. And also, a significant mass gets turned into these heavy elements. So that was a simulation. This is the sound, what it sounds like. This is real data. They're speeding up, they collide. And that's Bing, that's not real. That Bing is when they detected the radiation, the first one was gravitational waves. The Bing was where they detected gamma rays, and then just about every telescope on Earth looked at this thing after that, because this was an amazing event. So what happened was 100 million years ago, these neutron stars collided, spun up and collided. And there we see the evidence of it. And it's a proof that the speed of gravitational waves, which cause this thing, and the speed of light, which cause this, are almost the same. These signals traveled for 100 million years, and they arrived within 2 seconds of each other. So it's pretty good proof that of gravitational waves and of Einstein's theories. So in that 2 seconds, this is seconds along here, in that 2 seconds, it was estimated that about 1 Earth mass, or 2 Earth masses of gold, was produced. So you can imagine, I mean, this is like cosmic alchemy. We're not supposed to talk about alchemy anymore, but the alchemists actually had it right. If only they had a couple of neutron stars, they could make gold. So that's how you get the stuff, and where it ends up is in the galaxy, and as a mess. I mean, you basically all had all these stars throwing out stuff, and this is what you see. These are the stars that are behind, and these dark clouds are just clouds of rubbish left over. All the dirt, all the heavy elements. These are dark clouds left over from stars exploding, etc. So that's the ingredients. So how do you put it together? Well, gravity helps you there. This is a dark cloud, and you can see in the center, well, you can't see it because it's dark, a star has formed. So eventually gravity pulls all this stuff together that's remains of the stars, and you get the star, and you also get evidence of that through this. This is outflowing gas from the star, observed by ALMA, actually. So you're starting to form stars. At the same time as forming stars, you can form planets. And we know this now in the last 2 or 3 years through observations with ALMA and other telescopes in Chile, actually. Because if you look towards the center of these, you see evidence of planets. These are disks around stars, and you can see almost all of them have these rings. And these gaps, those gaps are clear evidence that something is clearing them, and these are young planets. These are all systems less than a couple of million years old, so they're very young as stars go. So they're all forming planets. They've all got planets around them. So what happens in these rings? Well, as I said, the clouds are full of bits of material, very small, usually dust, like grains of sand. But the grains of sand will eventually, under gravity and attraction, they come together and they form boulders. This is a simulation. They come together to form boulders, and then planetesimals, which are small planets. Rocky cores of planets. Eventually things get together and they collide and they accumulate and they stick to each other. There's some, I've glossed over, there's some bits of this which are really not understood yet, but This is generally the picture. And then eventually the rocky cores get mass enough and they start accreting the gas. And then you can get gaseous planets like Jupiter. But as well as things coming together, they also collide. Those collisions are really important in this system. The rocks are colliding, the boulders are colliding, the planets are colliding. But just to give you an idea of these are quite energetic events. In fact, in the early Earth, these collisions, you get bombarded with rocks and boulders all the time. These are pretty energetic events. Just to give you an idea of what it is, this is one that landed in Russia. A little rock, 20 meters across, tiny. But this is what it did. That's it going over here. That was a 20-meter rock going overhead. It was coming in. Sorry. It was coming in at about 15 meters per second. So it's coming in very fast. And there's a lot of energy. That's about as much energy as a small atomic bomb. Luckily, it was overhead. So most of the energy was dissipated in the atmosphere. But on the Earth, that sort of event would be continuous. There would be continuous events like that. But that's just a small thing. In those early solar systems, you get events like this. This is where a Mars-like object collides with an Earth-like object. It kind of messes up the Earth a bit. But this is important because this is how cores of planets form. We didn't fully understand. We still don't fully understand how in the Earth, the center of the Earth is iron mostly. How the iron gets all to the center of the Earth, and this is one theory that basically you get a lot of big collisions, and these will be relatively common. So you don't want to be around. So what's the results? Well, we know now we've actually now in the last 10, 15 years, about 4,000 planets have been discovered, and their numbers are going up all the time. This thing is a simulation. It's an orrery, actually, which is a simulation of all the planetary systems, or a large number of the planetary systems. The scale of the planets are obviously not that big, but you can see the orbits of the planets, and you can see the relative sizes. So these are Jupiters, the big ones, and down to Mercury, which is the tiniest ones. And the color is representing the temperature. So you've got some really hot Jupiters, which are sort of lava-like, 1,000 Kelvin or more. You've also got some cold systems, you've got cold planets, you've got hot planets, you've got a whole bunch of planets. Anyway, these are the real planets that have been discovered. Some of them, you can see some of them are going around really fast, and some of them, like, well, this is the solar system to scale. So, in the end, the interesting thing is that planets are really common, and they're extremely varied. The solar system contains some planets, but we've kind of been biased in the last few years up to what they are. But we now know that there are rocky planets like Earth. There are lava worlds, which now have very close. This is the planet plot of the year, how long it takes to go around the sun, against the size of the planet. And there are planets like Earth, which are very close to the sun. They're so hot that the surface will be lava. There are ocean worlds, which are basically like Earth, but lower mass, lower density, and warm enough for water. There are also ice giants, so basically they're the same as ocean worlds, but frozen. We know there are cold gas giants like Jupiter. There are also hot Jupiters, which are very close to the stars, and they're evaporating off their atmosphere. There's a whole variety. There's also this area under here, which we don't know about yet, but bigger telescopes now will find out. These are the distant things like Earth, which are around Earth-like stars, sun-like stars. But that's an interesting area if you want to think about life. Those are the planets that will maybe most likely to have life. So I've shown you some simulations. This is a real time-lapse image of a movie of some real planets. These are 4 planets. You can see them 1, 2, 3, 4 going around this star. This was taken over a few years, but you can see the orbits. These are planets. There's no doubt about it. So I think the take-home, we're not allowed to have bullet points, but I'm going to have one bullet point. Sorry about that. At least 10% of all stars have Earth-like planets. I mean, that's a pretty radical conclusion, because 20 years ago, Nobody knew any other planets apart from the ones in our solar system. So what does that mean for the number of planets in our galaxy? Well, here's a picture of our galaxy, or part of it. This was very recently released from the Gaia spacecraft. There are 1.7 billion stars in this picture. Actually, someone counted them. Well, the computer counted them. This is the exact number. It's not like, oh, we've estimated. These stars are individually measured. This is 1% of the stars in our galaxy. There are 250 billion stars in our galaxy. And I'll end up with a picture. Okay, so if you took, this is a picture of our galaxy. If you take another picture up here with the Hubble telescope, where there are no stars, or very few stars, and just stare at it for 50 orbits of the Hubble telescope. Okay, so there's a whole bunch of time. This is what you see. There are 2 stars in this picture. Somewhere, I can't even see them now. There's one there, and the other one's down there. You can tell them because they're the ones with the sort of crosses. The rest of them are all galaxies. So there are about 10,000 galaxies in this picture. So this is kind of giving you a feel for how many galaxies there are if you look deep enough. This is looking right back to the earliest galaxies. So in conclusion, I think the 3 take-home things are, we and planets are made out of destroyed stars, explosions. We're the remains of basically the mess that's left over after explosions, small and big explosions. It's actually easy to form planets. We know that because most stars have planets. And given that, then you can guess, well, you can estimate, I'll leave you to do the sum, how many planets like Earth there are in our galaxy, or in the universe. That's an easy number now. The difficult number is to work out what fraction of those have life, and that's talk for another day and someone else, I think. Anyway, thank you.